Nuclear transformations. Okay, so over the years, many nuclear transformations have been achieved. And basically what we mean there is we take naturally occurring isotopes and we add particles to them and transform or transmutate them into other types of isotopes. And one way that this occurs is by particle accelerators. And the name pretty much tells you what a particle accelerator is. It's a device that's used to speed up the velocity of particles or to make them go faster. And what that allows those particles to do then is when they're at those high velocities, they can overcome the forces of the nucleus and therefore bond in with the nucleus and transform or transmutate that particular isotope. Now, before 1940, the heaviest known element was uranium. And if we look on the periodic table, uranium has an atomic number of 92 and an atomic mass of 238.03. But in 1940, neptunium was produced by neutron bombardment of uranium-238. And now we have an isotope that's heavier than uranium. And since 1940, the elements with atomic numbers greater than 92 have all been synthesized by these processes. And all of these elements above element 92 are called trans-uranium elements. Now we want to deal with radioactive dating. And this is used to determine the age of a particular specimen. And particularly, we're going to talk about radiocarbon or carbon-14 dating. And this is basically a type of dating process that determines how old carbon-containing specimens are. So let's look at two reactions. Okay, here we've got carbon-14, which is transmutating into nitrogen-14 by a beta particle decay. And here we've got nitrogen-14, which is absorbing a neutron and forming carbon-14 and a proton. And if we look at these two reactions, the second reaction is forming carbon-14, whereas the first reaction was decaying carbon-14. And in nature, the rates of these two reactions are equal. And what that means is the amount of carbon-14 in nature is a constant. So if we look at living organisms that are constantly taking in carbon-containing compounds, their ratio of carbon-14 to carbon-12 will always be a constant. But when an organism dies, it no longer takes in carbon-14 atoms. And therefore, the carbon-14 that's in their bodies will start to go through that radioactive decay process. The amount of carbon-14 in the organism will start to decrease, and the ratio of carbon-14 to carbon-12 will start to go down. And the combination of that ratio change and the half-life for carbon-14 can be used to determine the age of a particular specimen. So let's look at an example. Okay, we've got this problem. It says the remnants of an ancient fire in a cave in Africa shows a carbon-14 decay rate of 3.1 counts per minute per gram of carbon. Assuming that the decay rate of carbon-14 in a freshly cut wood is 13.6 counts per minute per gram of carbon, calculate the age of the remnant. And it tells us again that the half-life of carbon-14 is 5,730. So the key to this problem is the fact that the decay rate is proportional to the number of atoms. So we can use the decay rate to find out what the ratio of the atoms are for carbon-14 and carbon-12 in that specimen. Now, radioactive decay is an integrated first-order rate law. So we can use equations that we know for integrated rate laws to calculate how old this particular specimen is. And the first thing we can do with an integrated first order rate law is we can calculate what the rate constant K is. And for a first order reaction, K is calculated by taking 0.693 and dividing it by the half-life. So 0.693 divided by 5,730 will give us a rate constant of 1.21 times 10 to the negative 4 for carbon-14. Next, we're going to look at the integrated rate law equation, which is the natural log of the concentration after a particular amount of time equals negative K times the time plus the natural log of the initial concentration. And again, we need to remember that the decay rate is proportional to the amount of material that we have. So we can manipulate this equation a little bit. We're going to subtract the natural log of the initial concentration of A from both sides, and that'll give us the natural log of A minus the natural log of A initial equals negative KT. And we can manipulate this a little bit more and say the natural log of A divided by A initial equals negative KT. Now we can plug in the numbers. And again, because the decay rate is proportional to the number of atoms, we can plug in the decay rates. So the natural log of 3.1 divided by 13.6 will equal our negative K value, which we calculated, 1.21 times 10 to the minus 4 times time. So we'll plug those values into the equation to solve for T, and T is going to equal 12,000 years. So this particular ancient piece of wood is 12,000 years old. Now we need to talk a little bit about the stability of the nucleus of a particular isotope. And we can determine that stability by looking at the potential energy changes that occur when a nucleus is formed from its protons and neutrons. So we're going to look at an example. Let's say that we want to find out what energy is associated with the formation of oxygen-16 nucleus from 8 neutrons and 8 protons. So we would have 8 neutrons plus 8 protons will give us oxygen-16. And we can look up on the table what the mass of a neutron is and what the mass of a proton is, and we can calculate what the mass of this nucleus should be. So we'll take the mass of 8 times the neutrons plus 8 times the protons, and that will give us the mass of that nucleus. So 8 times 1.67493 times 10 to the minus 24 grams plus 8 times 1.67267 times 10 to the minus 24 grams, and that'll give us the mass of that nucleus of 2.67804 times 10 to the minus 23rd. Now, if we're told that the actual mass of a carbon-16 nucleus is 2.65535 times 10 to the minus 23 grams, we're going to notice that there's a loss of mass. And we're going to want to calculate what that loss is. So we're going to take the mass of the actual oxygen nucleus and subtract the calculated mass for that oxygen nucleus. And that's going to give us negative 2.269 times 10 to the minus 25 grams of mass that's lost when that nucleus is formed. So we need to deal with where that mass goes. So first we're going to calculate that value in terms of a mole of oxygen-16 atoms. So we'll just do a little conversion. We'll take that negative 2.269 times 10 to the minus 25 grams per nucleus, multiply it by Avogadro's number, so 6.02 times 10 to the 23rd nuclei per mole, and that'll give us a value of negative 0.1366 grams per mole. Or if we can convert that to kilograms, we get negative 1.366 times 10 to the minus 4 kilograms per mole. Now we're going to look at where that mass actually goes. And what we're going to be dealing with is that E equals mc squared value, where the mass is actually going to be converted into energy. So we take that negative 1.366 times 10 to the minus 4 kilograms per mole, multiply it by the speed of light, and there should be a square here, so the speed of light squared, and that's going to give us negative 1.23 times 10 to the 13 joules per mole. Now, where the joules come from is we get kilojoules meters squared per second squared, which is a joule per mole. And when we look at the value, it's a negative value. So that negative value tells us that energy is going to be lost from the system, or it's an exothermic process when we form that nucleus from its protons and neutrons. Now, what we want to deal with next is kind of the opposite. We're going to talk about the nuclear binding energy, which is calculated the same way, it just has an opposite sign. Because the nuclear binding energy is going to be the energy that's required to break down a nucleus. And that process would be endothermic. So we'll look at an example again. A little bit of a difference this time because now we're going to be given AMUs instead of grams like we did in the last problem. So this time we're going to calculate the binding energy per nucleon, that just means per particle in the nucleus, for helium-4. And it tells us that the atomic mass for helium-4 is 4 AMUs, and the atomic mass for a proton is 1.01 AMU. So the first thing we're going to want to do is we're going to want to calculate what the change is in our mass. So we'll find out what the mass of that helium nucleus is, which is the 4.00, and we'll find out what the mass should be. So we'll look up on the table what the AMUs are for a proton and a neutron, and we know that helium is 4.00 AMUs. So we'll take 2 times 1.0078 AMUs, and that's for our proton, plus 2 times 1.0087 AMUs, which is for our neutron. And again, these values just came off the table. We'll subtract it from the AMUs for a helium nucleus. And again, we're going to notice that we lose mass. And that's AMUs per nucleus. So we're going to do a little bit of conversion. We're going to convert that from AMUs per nucleus to kilograms per nucleus. And again, we're going to get this value off of a table. It relates AMUs and kilograms, 1.66 times 10 to the minus 27 kilograms per AMU. So that's going to give us a change in mass of negative 5.04 times 10 to the minus 29 kilograms per nucleus of helium. And now we'll convert that mass lost to energy. We'll plug in the negative 5.04 times 10 to the minus 29 kilograms per nucleus in for M. We'll plug in 3.00 times 10 to the negative 8 meters per second, and we'll square it for the speed of light. And that's going to tell us that that value is negative 4.54 times 10 to the minus 12 joules per nucleus. And again, it's kilogram meter squared per second squared is where that joules would come from. It's a negative because this value is actually telling us the energy that's being released when the nucleus forms. So we would make it a positive value, and that would tell us how much energy has to be absorbed to break apart that nucleus. And then the question actually wanted us to solve for the binding energy in terms of nucleons. So we would take that 4.54 times 10 to the minus 12 joules per nucleus and divide it by 4 nucleons per nucleus, because when we look at helium, it has 2 protons and 2 neutrons. And that'll give us 1.14 times 10 to the minus 12 joules per nucleon.